Hey, it's Abdul. Welcome to another video of the BIOSTATS CRUSH course. Today, we're going to be going over hypothesis testing. Now, this is going to be a bit of a woozy, right? I really want you to lock in this one because this is something that gets tested quite a lot in the MBME exams and also is something that might not be the most intuitive concept, but I hope I'll be able to explain this topic in a nice and smooth way. So, one of the goals of science, one of the goals of research is to determine whether something really caused something else, right? If thing A really did cause outcome B, or was it due to chance? Or if treatment A really is better than treatment B, or again, was it due to chance? Now, in order for us to do that, we can use the help of biostatistics to calculate the mathematical probability that something is caused by chance. And as always, the best way to understand this is going through a goofy example. Let's say you've heard a lot from your aunties and your grandma and old Mima that drinking milk is gonna make you tall. You gotta turn you into peak prime LeBron James.
You are my sunshine, my only sunshine. You make me happy when skies are gray.
So you decide to do a study to look at whether drinking milk actually makes you tall. And you do the regular study. You get a group of people, you make them drink milk. You get another group of people, you don't make them drink milk. And then you compare their heights. And let's say that this study is done and the biostatistician tells you, hey, okay, finally the results are out. The effect of drinking milk on height has a probability of 0.76. This means that we use mathematics, we use biostatistics to come to a conclusion. And what that actually means is that there is a 76% chance that the increased height in milk drinkers was actually due to chance and not due to drinking milk. And that obviously is very profound because it tells you a lot of things. It tells me, as someone who's lactose intolerant, that it's probably not a good idea to drink milk if I want to get tall. Now, hypothesis testing really kind of revolves around these three things, right? You make a hypothesis, you do some hardcore nerd maths, and then you interpret those results. And obviously, those hardcore nerd maths, they're really outside the scope of this playlist and outside the scope of step 1, step 2, and step 3, but it's just something that you want to know about. Now, one thing that you should know is what are the things that increase or decrease the probability that the effect that you see in this study or in this trial is due to chance or not. And there are actually three things. One of them is the difference between the means of the two groups. Number 2 is the scatter of data. And number 3 is the number of subjects, aka the sample size. Now, obviously, this is a lot of words and it's a bit boring. So let's run through our second goofier example. So, word on the street is that there is this new neuromarker found within the CSF fluid called BS3.2. And BS3.2 was seen to be elevated in people who were full of crap. So, the big question is this elevation due to chance, or could it be that BS3.2 is a good prognostic marker? So, you decide to do a study. You take a randomized control trial, you grab a random sample of 100 people, then you grab a sample of 100 healthcare insurance CEOs and you measure their BS3.2s, and you'll find out that the mean in the normal population was around 1 milligrams per deciliter and the mean in the CEOs is around 12 milligrams per deciliter. So now the big question that we have here, the conundrum, is this elevation due to chance or is there actually a true association? This is where hypothesis testing comes in. And this is also where we're going to demonstrate those three factors that influence the probability that this is due to chance. The first one was that the higher the mean difference, the lower the probability that what we see is due to chance. And you can see that on the image there. If there's a big difference between the two groups, if there's a big difference between those means, that means that it's probably not due to chance, and the opposite is true. So let's assume that the difference between the two groups was the mean in the normal population was 7 milligrams, and in the CEOs it was around 8 or 9. That's not a big difference. So that is more likely to be due to chance than not. Another example of a factor that influences the probability is the scatter, right? Which is another way of saying the standard deviation of the data that we have. The greater the standard deviation, the more of an overlap we have, the higher the chance that this finding is due to chance. And the opposite is true. The lower the scatter, the more clustered those data are around that mean, around that measure of central tendency, the lower the probability of it being due to chance. And finally, the higher the sample size, again, the lower the probability of chance. The more data entries you have, the more confident you can be that what we are seeing is due to the true effect and not due to it being just random chance alone. Now, you may notice that out of those three factors, the only one that we can control is the sample size. We can't really control the difference between the means because that's a result. We find out after the end of the trial. And it's the same thing for the scatter of data. Again, we can't really control that standard deviation, but what we can control is the sample size. The larger the sample size, the lower the chance that if we find a difference, that is going to be due to chance. Now, once you explore this topic a bit further, you will hear this term thrown quite a lot, and that is going to be the null hypothesis. What the null hypothesis is going to be a statement that says that there is no relationship between two variables, right? Either between an exposure, an outcome, or anything like that. And that's by convention. That's going to be the null hypothesis. The alternative hypothesis, also written as H1, is that there is a relationship between two variables. So going back to our example earlier, the null hypothesis of our study is that there is no relationship between BS 3.2 and being full of crap, and the alternative hypothesis is that there is a relationship between BS 3.2 and being full of crap. So this is just kind of like the standard notation of how we describe hypotheses. Now, whenever you do a study, whenever you do a trial, there are really 4 outcomes that can occur related to your hypothesis, and the best way to kind of really understand this is by this magic 2x2 table that has the experiment results on the left hand side on the y-axis and reality on the upper x-axis. So let's dissect this and understand it a bit further. When you do an experiment, you can have 2 outcomes. The results will either show that there is a difference between the 2 means, so we accept the alternative hypothesis, or we find that there is no significant difference, so we accept the null hypothesis. And the reality is that it could either actually be a difference between these 2 variables, or it could be just due to chance. So let's say we run a study and we find that there is a difference, and in reality there is a difference. This is pretty nice. And also, let's say we do a study and we find that there is no significant difference, and in reality there is no significant difference. This is also pretty nice. Now imagine, however, that we do a study, we find a difference between these 2 kind of variables or outcomes, but in reality there is no difference. This is known as your type 1 or alpha error. It's like going to a dude and being, hey, listen man, we ran a pregnancy test and it was positive. And very obviously that the person is not pregnant. So this is going to be a type 1 or an alpha error. Alternatively, you may run a study and find there is actually no difference between the 2 groups, but then in reality, there is a difference. This is known as a type 2 or a beta error. So this is kind of like the table all filled out. These are the 2 options. You may have either 2 outcomes which are accurate, and then you can either have a type 1 or a type 2 error. Now, type 1 alpha errors, these are usually due to chance, and if they happen, it's just like tough luck. But type 2 or beta errors, these are usually due to a low sample size. And that makes sense when we spoke earlier about those factors that can influence the probability of chance. If the sample size is too small, we may not detect a significant difference statistically, but there actually might be a difference in reality, but that's just because we're limited by that small sample size. Now, re-exploring that table, going back to the outcome where we found a difference between the 2 groups, and there is a difference between the 2 groups, that's actually also called the power, the statistical power. And what statistical power is the ability to correctly reject the null hypothesis. And we know that when we draw a 2x2 table, the numbers usually add up to 1. So the power is also 1 minus your type 2 error. When designing clinical trials, when designing studies, we usually set this power ourselves. We try to set it around 80%, and this is done by playing around the sample size. Obviously, the nitty-gritty details is way out of scope, but that's everything that you need to know about statistical power. Now, around this time, the monkey of questioning pops up and is like, hey, how do we know whether to accept or reject the null hypothesis? And that's actually a great question. It's through one magic word, something that I'm sure you already have heard many times before, and that is going to be the p-value. So what is a p-value? A p-value is the probability that the observed data that you see in front of you is due to chance alone. So to give you an example, if I tell you something has a p-value of 0.03, this means that the probability that this effect happened due to chance is going to be 3%. And by scientific convention, most medical papers will set a p-value of 0.05 to be significant. So if the p-value is greater than 0.05, we are not confident enough to accept the alternative hypothesis. So we will accept the null hypothesis and say, oh, the difference is due to chance, because 5% is pretty high, right? It's 5 out of 100. If the p-value is less than 0.05, and this is where researchers get super happy, that means that the probability that this is due to chance is very low, and we reject the null hypothesis, and that's usually happy monkey time. So going back to our study, our trial, we find out that the biostatistician did some tests and was like, yo, the p-value for this two means is 0.073. This means that the chance that this was due to chance and randomness alone is 7.3%. So our conclusion from this trial is that the difference in the BS3.2 neuromarker between the normal population and those health insurance CEOs was due to chance alone, and the search for a better surrogate marker continues for another day. And with that, we are done with hypothesis testing. Thank you so much for watching till the very end. I hope this was not too exhausting, but thank you. And we are now reaching the end of section 1 of the BIOSTATS CRUSH course, so good job for making it this far. Thank you so much for listening and watching, and if you did find this video helpful, please leave a like, comment for any ideas or any questions, and subscribe to see more of this content. And of course, hit the bell icon if you want to be the first person to type first in the comments. But in all seriousness, thank you so much for watching. If you're interested in mentoring, whether for step 1 or step 2, do reach out. Use the code KLED, that's KLED, for 20% off of your first mentoring session. That's going to be for the first 5 people who use the code. Thank you so much for listening, and wishing you a beautiful, beautiful day.